Okay, so now we have our geometry imported and we're ready to begin the analysis. So if I go into the geometry now, you can notice that I have two separate bodies. And in finite element analysis, if you have a separate body, that's a separate mesh, and you have to tell it how those meshes are going to interact. So we're going to look at that under connections. So in the we can see here that ANSYS has already defined a contact region for us. And we can see in the red and the blue the two areas, and again it's color-coded to the contact and target bodies. And what's happening is the contact surface is they're looking for penetration of any of the nodes into the target body. And if it does, then it has to solve for a force to resist that and the appropriate deformation. This is substantially more complex than doing a standard problem. And the simplest thing to do is to pretend those are bonded together. And if the stresses are, that's not an area particularly important, then that can be an adequate assumption. And that's what this defaults to. And so I would suggest first solving it with the bonded option and then explore some of the other options. And we'll look at that in a minute. Mesh, you've seen some basics of meshing here. Now you can, again, you can apply principles of refinement. You may want to pay close attention to how much elements you have in the contact area. Refining there could be profitable. Note that these features, and particularly the fine fillet radii in here, could pose a challenge. Now, I'm just going to show you the basic idea. I want you to think about how you might do this and do this better. So I'm going to show you kind of a basic solution. So as before, we can come in here and apply our supports. And I'm going to put displacement. I'll select this face here, and I'm going to fix that in all axes. I could have done that with a fixed support. So that's not going anywhere. At that end, these two pieces are glued to each other, so they're good. And I'm going to use, go ahead and generate the mesh. Alright. That is a very coarse mesh. And one thing to keep in mind, one of the benefits of a coarse mesh is it lets you check the validity of your constraints and without having a model that's going to take 5 or 10 minutes to solve, only to find out that there was a constraint issue. So I need to apply a force on here, over like that. Let's go back and apply a load, put a force, and I'll just apply this to the face. So let's select face, and do that by component, easier. So that's in the y-axis. We'll do minus 250 pounds. Now I forgot. Let's see, did I hit apply there? Okay, so now that moved over there. So I've got force, displacement. Oh, I didn't select that face. So select it, hit apply. Okay. And so let me add in some things for solution. Add in equivalent stress. If it's a ductile material, would be a good failure criteria. It's always nice to find the deformation. Now sometimes it may be helpful to see the directional deformation. Say, let's look at the y-axis. That's where we'd expect to see most of it. It might help you detect if there's a constraint problem, if it's moving in a way that you don't expect it to. And there's a tool here, we add a stress tool, and that allows me to plot safety factor. If I come up with a stress tool, you can pick the failure theory that you want to use, and including the Moore Coulomb, which is similar to the modified Moore for brittle materials. And you can select whether you're going to do it based on tensile or ultimate material properties. So that'll be a useful factor. And Let's go ahead and solve. So I paused that a little bit there because it took a few seconds. We can plot our stresses, and we can see that there are high stresses on the surface. There's probably some peaks up here. That mesh is probably too coarse to be able to really see what's happening at that fillet. I would need to do some local refinement in order to do that. So that's a basic solution. Now, one thing I want to show you is looking at other contacts. I can come back to the contact region. In reality, this is a slip fit. There's friction, so I can assume friction, and we'll do 0.15, kind of metal on metal. If you're going to do a rough can be good. That allows it to do high friction contacts. Frictionless, you need to be concerned about whether it's going to be stable in the solution. But going to a contact point there, it starts to become nonlinear, and so the solution time is likely to increase. Okay. And one of the things that can help the interface treatment is to adjust to touch, so that it makes it a little quicker to find the contact point. It doesn't have to hunt for as much, which has some instabilities around it. So we go ahead and we'll resolve that, see if we're adequately, if it'll solve. Okay, so this, we've got a pivot warning, which likely relates to some instability. And also it didn't solve. So one thing I'm going to try here is to help avoid the slipping down there, is I'm going to constrain the z-axis in the right along that line. Since that some concern, I don't know if for sure that's a great idea, but let's give it a try. Put Z0. And we'll resolve. Now there could also be issues with how much constraints, but I do know, because it solves successfully with a bonded, I know that the arm, this first part, is successfully constrained, and so the problem is in the constraint on the second part. And again, I didn't get a good solution there. So we look at our messages, similar messages before. So I did a little experimentation, and after trying a few different things in the friction setting, I refined my mesh, and after which I was able to get a successful solution to the analysis. And that reiterates the point that the mesh can play a role in solving that. In this case, I just did a global refinement. I'm sure you'll have smarter things that you can do, but you can kind of see a little bit of the stresses and how they're distributed. You may want to think about whether that's consistent with the loads that you'd see on there. It may be helpful sometimes in thinking about directionality, is to put stress in a particular direction in order to be able to see. For example, we could put z-axis in there, because that's some of where your intuition is. That may help you to be able to validate the solution. So here you can see that you have tensile stress on the top and compressive stress on the bottom, as you might expect to have for and a little bit of stress up there at the tip. but that would be kind of what you'd expect for the parts. Now, the other thing that we can just remind you of, in order to really see what the stress here, we may want to define a section plane. So I could define a plane and now if I grab this, select the selection plane, I can do the tool, I can drag it back and forth, rotate this around so I can see how the stresses are through the cross section. And you can even define a second section plane. Now I can look at the other direction as well, and if I move this, you can begin to see what the stresses are at any of the locations where you might be interested. Okay, so there's a couple thoughts on there. Again, basic starting point, you look for how you think would best to do it, and apply some engineering judgment in order to get the best solution you can in a limited amount of time.